Welcome to AI Paper Podcasts. We are diving straight into a newly published paper from March 2, 2026, titled CUDA Agent, Large-Scale Agentic RL for High-Performance CUDA Kernel Generation, brought to you by researchers from ByteDance Seed and Tsinghua University. Here are the key insights you need to know right now for this short-form edit. While general-purpose large language models struggle with the highly specialized task of writing and optimizing pseudocode, this paper introduces CUDA Agent. It is a large-scale reinforcement learning system that fundamentally improves an LLM's intrinsic ability to write highly optimized pseudokernels. It does this through a three-part system: a scalable data synthesis pipeline, a skill-augmented execution environment for automated profiling, and stable RL techniques, including rejection sampling fine-tuning. The benchmark results are staggering. On KernelBench level 1 and 2, CUDA Agent achieves a 100% faster read over torch.compile and 92% on level 3. On the hardest tasks, it outperforms top proprietary models like Claude Opus 4.5 and Gemini 3 Pro by about 40%.
Which, honestly, for the ML engineers and AI researchers tuning in who know firsthand how incredibly painful writing custom kernels can be, this represents a massive leap forward in automated hardware optimization.
Yeah, that was the dense rapid-fire summary. Let's take a breath, shift gears, and really unpack how the researchers actually pulled this off. Because you and I both know that GPU kernels are the absolute bedrock of modern deep learning infrastructure.
Totally.
But writing high-performance CUDA isn't just about knowing basic C++A. You have to have this incredibly deep micro-architectural knowledge of NVIDIA hardware, memory hierarchies, and sophisticated profiling toolkits.
Right, and visiting LLMs largely fail here because of the exact complexity. I mean, they're fantastic at general software development. You can ask a frontier model to spin up a web app or write a Python script, and it performs basically with human-comparable proficiency.
Oh, easily, yeah.
But when you asked an off-the-shelf LLM to write a complex CUDA kernel, it usually just gets destroyed by automatic compiler-based systems like torch.compile.
Which feels intuitive, right? Considering compilers have decades of determinism and optimization heuristics baked right into them.
Exactly.
But researchers have definitely tried to use AI for this before. When you look at prior works like Stark or Evo Engineer, why didn't those approaches crack the code?
Well, those earlier attempts definitely made progress, but they suffer from some fundamental architectural flaws. They generally fall into two camps. They either use training-free workflows, meaning they rely on hand-designed search heuristics guided by execution feedback, or they fine-tune models within these fixed multi-turn execution loops.
Okay.
The underlying issue, though, is that these methods just hit the ceiling of the base model's existing knowledge.
So they aren't actually teaching the model to be a better CUDA programmer natively. They're just kind of forcing it to guess and check until it gets exhausted.
Yeah. They end up wasting massive amounts of context length by including all the previous failed solutions in the prompt. But more importantly, they fail to improve the base model's intrinsic CUDA optimization abilities. They constrain the agent's autonomy to actually learn debugging and profiling strategies on its own. So the ByteDance and Tsinghua researchers realized that to fix this, they needed to build a system from the ground up, focusing heavily on the training data, the interaction environment, and the stability of the reinforcement learning phase.
Let's look at that first massive hurdle then, the data drought. Because if you want to train an RL agent to write expert-level CUDA, you need a massive amount of training data.
You do.
An expert-level CUDA reference code isn't exactly lying around on GitHub in huge quantities. Plus, paying human experts to write it manually is just prohibitively expensive. So how did they get around this bottleneck?
They built a scalable data synthesis pipeline that is honestly brilliant in its simplicity. They started by crawling standard PyTorch and transformer libraries to build a repository of fundamental seed operators. We're talking about your basic matrix multiplications, convolutions, ReLUs, things like that.
Right, the building blocks.
Exactly. Then they used an LLM to perform what they call combinatorial synthesis.
Combinatorial synthesis. Are they just stacking these basic operators together to make bigger ones?
Yeah, they stacked anywhere from 1 to 5 PyTorch operators to create fused tasks. So instead of asking the model to just optimize a matrix multiplication, the LLM generates a problem that requires a matrix multiplication followed by a division, a summation, and a scaling operation, all presented as one single fused task.
I was reading about this fusion process, and it seems like it's doing a lot more than just chaining operations end to end. Why does fusing these tasks matter so much for training the model?
Because it completely reshapes the optimization landscape. If you just chain operations sequentially, the hardware has to write the output of the matrix multiplication to the GPU's global memory.
Which is slow.
Incredibly slow. It has to write it, then read it back for the division, write it back again, and read it back for the sum. That trip to global memory is super inefficient. Fusion forces the model to learn how to keep intermediate results in shared memory or directly in the thread registers.
Oh, I see.
It teaches the model about occupancy constraints and how to map parallel layouts efficiently. It takes a simple math problem and turns it into a highly complex, realistic CUDA optimization puzzle.
But if you're just randomly mashing PyTorch operators together, aren't you going to generate a lot of garbage data, like things that don't even make mathematical sense? How did they ensure the quality of the synthetic training data?
So they implemented a really strict filtering process with 4 main criteria. First, the data obviously has to be executable in both eager mode and compile mode. Second, it has to be non-stochastic. There can be no inherent randomness because you need reproducible deterministic execution times.
Right, you can't optimize what you can't reliably measure. Real quick, though, before we go further, for anyone listening who might be a bit fuzzy on the terminology, what's the practical difference between eager mode and compile mode when the agent is testing its code?
Sure. PyTorch eager mode evaluates operations line by line exactly as they're written in Python. It's great for debugging, but it has a ton of Python overhead. Compile mode, specifically torch.compile, captures the entire computational graph ahead of time and applies advanced compiler optimizations to run the whole block of code much faster. So the data had to run both.
Okay, makes sense.
Third, they restricted the execution time in eager mode to be strictly between 1 millisecond and 100 milliseconds.
I imagine that filters out the trivial tasks that are too fast to optimize meaningfully and the excessively heavy tasks that would just bottleneck the entire training pipeline.
Exactly. It keeps the training efficient. But the fourth criterion is the most fascinating one. They implemented anti-hacking checks.
Anti-hacking. Are we worried about cybersecurity here, or is the model doing something else?
No, it's about reward hacking. An AI agent will always find the path of least resistance to a high reward. If the inputs to a synthetic function are predictable, the model might just figure out the answer and output a hard-coded constant value to bypass the computation entirely.
Oh, wow. So it just skips the math.
Yeah, that would give it a blazing fast execution time, but it wouldn't have learned anything about CUDA. So the anti-hacking check verifies that outputs for different random inputs aren't just constant values or numerically indistinguishable.
That is wild. Okay, so they built this massive, high-quality synthetic data set of complex fused operators. But the agent isn't just writing code blindly into a text editor. It's using a structured environment. Okay, let's unpack this. How does the agent actually interact with this data?
The researchers adopted an agent skills paradigm. They equipped the model with a structured specification that formalizes how to write, validate, and optimize CUDA kernels. The environment provides automated test scripts. When the model writes a kernel, the environment attempts to compile it, runs it, and feeds the compilation errors, the runtime failures, and the actual profiler feedback straight back to the agent.
So it's a true multi-turn interaction. For reinforcement learning to actually work, though, you need a highly tuned reward signal. You have to tell the model exactly what good looks like. How does the reward math break down for the agent?
It uses a very elegant 4-tier system, assigning a reward score between -1 and +3. If the correctness check fails, meaning the code doesn't compile or it produces the wrong math, it gets a -1. If it's correct but slow, it gets a +1.
So it's heavily encouraged to at least write working code before it tries to be clever.
Right. Then, if it's correct and significantly faster, specifically greater than a 5% speed up over PyTorch eager mode, it gets a +2. But the ultimate goal, the +3 reward, is only given if the generated kernel beats both PyTorch eager mode and torch compile.
So torch compile is essentially the final boss it has to defeat to get the maximum reward.
Exactly.
The researchers ran an ablation study on this multi-turn environment. What happens if you take that profiler feedback away?
Well, they trained a baseline model using just single-turn code generation. No execution feedback, just predicting the final kernel in one shot. Without that multi-turn interactive agent loop, there is a substantial drop in both correctness and optimization. In fact, without seeing the compilation errors and profiler feedback, the kernels generated by the model actually regress in performance. The agent needs that interactive loop to diagnose memory bottlenecks and refine transformations across multiple turns.
It's learning to use the profiler just like a human performance engineer would. That is crazy. But behind the scenes, getting this RL training to actually work was not smooth sailing. Initially, the training just completely collapsed. What exactly happened?
Yeah, during their initial reinforcement learning trials, the training collapsed after just 17 steps. The model's performance tanked entirely, and the training reward plummeted to zero.
17 steps is nothing in the context of training a massive LLM. What was the root cause of such a catastrophic failure?
It comes down to a severe domain distribution mismatch. Think about the pre-training data for a standard large language model. You have petabytes of Python, JavaScript, English text, but highly optimized CUDA C++ code. That makes up less than 0.01% of standard pre-training datasets like the Stack or StarCoder.
The model barely knows what CUDA looks like natively compared to its knowledge of something like Python.
Right, and because of this massive gap, when the model tries to generate CUDA code, it produces a lot of low probability tokens. In proximal policy optimization, or PPO, the specific RL algorithm they're using, this wreaks havoc on the importance sampling ratio.
Wait, hold on. Importance sampling ratio. What exactly does that mean for you when you're actually running this training, and why does it break the system?
So in PPO, you are constantly comparing the probabilities of the actions taken by your new updating policy against your old reference policy. The math involves dividing one probability by the other. When the training engine and the inference engine use different numerical precisions like BF16 versus FP16, those extremely low probability tokens create small numerical errors right near the precision floor of the hardware.
I think I need an analogy for this. Is it like a rounding error?
Perfect analogy. Imagine you are running a massive financial spreadsheet for a multinational corporation. If you have a rounding error of a fraction of a cent on $1 million transaction, it doesn't matter. But if you are dividing by a number that is incredibly close to zero, which is what happens with these low probability tokens, that tiny rounding error suddenly blows up into a massive number. It cascades through the spreadsheet and destroys your entire budget. In PPO, this causes massive variance in the importance sampling ratio, which essentially breaks the mathematical stability of the RL update.
So how do you stop that collapse? How do you get the model to stop generating those mathematically dangerous low probability tokens?
The researchers introduced a multi-stage warm-up using a technique called RFT, or rejection sampling fine-tuning. Before doing the full PPO reinforcement learning, they used a base model to sample a bunch of trajectories in the environment. They filter out all the bad ones, the hallucinations, the invalid behaviors, and they used standard supervised fine-tuning exclusively on the successful high-quality trajectories.
Oh, okay. So they are seeding the model with a solid baseline of competent behavior before letting it explore the vast optimization space on its own.
Exactly. RFT provides behavioral prior. The researchers showed that without RFT, the policy entropy surges. Entropy in this context means the model gets confused, its probability distribution flattens out, and its outputs become diffuse, incoherent, and unstructured. By applying RFT first, they achieved strict entropy control. They successfully stabilized the PPO training up to 150 steps, showing consistent, steady reward growth.
We should definitely mention the sheer scale of what they're running here to achieve that stability. The base model they used is Seed 1.6, which is a massive 230 billion parameter mixture of experts model. Why go with a MOE architecture here instead of a standard dense model?
Well, with mixture of experts, you have massive total parameter capacity, but you only activate a small subset of expert neural networks for any given token. This is perfect for a highly specialized domain like CUDA. The model can dedicate specific experts to deep C++ syntax and memory management without degrading its general reasoning and logic capabilities, which it still needs to understand the algorithmic structure of the PyTorch code.
So they took that 230 billion parameter MOE, scaled the context length to a massive 128K tokens, and during evaluation, they allowed the agent up to 200 interaction turns. That is an enormous amount of compute dedicated to optimizing a single kernel.
The compute investment is massive, but the benchmark results completely justify it.
Let's get into those benchmark results. The researchers evaluated CUDA Agent on KernelBench, which is split into different difficulty tiers. On level 1 and level 2, which are the basic and intermediate tasks, CUDA Agent hit a 100% pass rate and a 100% faster rate compared to torch.compile. It achieved geometric mean speedups of around 2.8x to 3.27x over the compiler.
Compilers are deterministic and highly tuned over decades. Beating them across the board on level 1 and 2 is a major achievement for an AI system. Level 3 is where the real complexity lives, though.
Right. Level 3 has highly complex real-world operators that you'd find in production models. Even their CUDA agent hit a 94% pass rate and a 90% faster rate versus torch.compile. To really put this into context, we have to look at how the proprietary giants performed on these exact same benchmarks.
They tested top-tier proprietary models like Anthropic's Claude Opus 4.5 and Google's Gemini 3 Pro. These models are incredibly sophisticated and have vast knowledge bases. They had decent pass rates, meaning they could write code that functionally worked and didn't crash, but their faster rates were terrible. On level 3, Opus and Gemini only managed to beat the compiler about 50% to 52% of the time.
So nearly half the time, the code written by the smartest proprietary models in the world was actually slower than just running the standard PyTorch compiler.
Yeah, CUDA Agent outperformed Claude Opus 4.5 and Gemini 3 Pro by roughly 40% on that level 3 split. General-purpose models simply cannot compete with an agentic system that has been explicitly trained with direct profiler feedback to understand memory bandwidth and physical hardware constraints.
I have to mention a hilarious aside from the footnotes of the paper. They couldn't even evaluate the ChatGPT-5 models versions 5, 5.1, and 5.2 because the models consistently declined to respond to CDA-related prompts. They just refused to participate in the benchmark.
It highlights how highly specialized and potentially fragile this domain is. If a general model hasn't been safely aligned or explicitly trained to handle raw, low-level hardware interactions, its internal safety filters might just trigger a refusal, or it might completely fail to engage with the prompt.
What does this all mean for you when you are actually building systems? What is the code actually doing to get these massive speedups? Let's get under the hood with some case studies because the engineers listening want to know the tricks the agent is using. I was looking at the first case study in the paper involving algebraic simplification, and I couldn't believe how it bypassed the compiler just by rethinking the math.
Oh yeah, in a level 1 task, the goal was to multiply a diagonal matrix by another dense matrix. The standard PyTorch reference code explicitly constructs that diagonal matrix in memory, filling it mostly with zeros, and then runs a generic heavy matrix multiplication over the whole thing.
Wait, constructing a mostly empty diagonal matrix in memory sounds horribly inefficient, doesn't it? That scales terribly as the matrices get larger.
It does. The time complexity for that generic multiplication is O(n) squared m. It is doing a tremendous amount of unnecessary work multiplying by zeros. The CUDA agent looked at the problem and realized that mathematically multiplying a dense matrix by a diagonal matrix is equivalent to just scaling each row of the dense matrix by the corresponding scalar value from the diagonal.
So it just skipped the intermediate matrix construction entirely.
Completely. It wrote a custom kernel that performs purely row-wise scaling. It dropped the time complexity down to O(n) m. The result was a 73.31x speedup over torch.compile. The agent bypassed the compiler's generic optimizations by applying high-level algorithmic and algebraic reasoning before it even wrote the CUDA syntax.
That is beautiful. Moving to the fuse tasks, there was an example where the agent had to handle a matrix multiplication followed by a division, a summation, and a scaling factor. How did it optimize that beyond just putting it all in one file?
The agent fused all of those disparate steps into a single unified kernel. It specifically used shared memory on the GPU for intra-block reductions. This means the individual threads within a single block cooperate to sum up the values locally without having to constantly talk to the slow global memory of the GPU. It also utilized float-4 vectorized loads to maximize memory bandwidth utilization, reading 4 floating point numbers at a time from memory instead of one by one.
It's writing C++ like a senior NVIDIA engineer. The case study that really caught my attention, though, was on a level 3 task, a ResNet basic block. This isn't just a toy math problem. This is the core building block of massive vision models.
A standard ResNet block is complex. It involves convolutions, batch normalization, residual connections, and ReLUs. First, the agent did something incredibly clever in Python before it even touched the CUA code. It folded the batch norm parameters directly into the convolution weights.
Take a second to explain folding so we can picture what's happening mathematically.
Sure. Batch normalization applies a specific scale and shift to the data to keep it stable during training. But during inference, those scale and shift parameters are completely static. Because they don't change mathematically, you can just pre-multiply those static numbers directly into the weights of the preceding convolutional layer. The agent did this autonomously, which completely eliminates the batch norm operator from the computation graph. It just ceases to exist at runtime.
That alone saves memory bandwidth and the overhead of launching a separate kernel, but the agent went deeper into the hardware, didn't it?
Well, it dove directly into the C++ CUDA wrappers. It used a specific, highly optimized CUDA function convolution bias activation forward to fuse the convolution, the bias addition, and the ReLU activation all into a single hardware-accelerated pass. To top it all off, It explicitly enabled TF32 computation in the code.
Wait, what is TF32? Is that a specific data format?
TF32 stands for TensorFlow 32. It's a special math mode built into modern NVIDIA GPUs, like the Hopper architecture. By explicitly enabling TF32, the agent told the execution engine to leverage the specialized tensor cores physically built into the silicon. It recognized that for this specific neural network block, slightly lower precision arithmetic was perfectly acceptable for the final result, and it actively turned on the hardware feature that makes it run exponentially faster. The final result for the ResNet block was a 3.59x speedup over the compiler.
It's bridging high-level algorithmic graph transformations, like folding the batch norm, with low-level hardware-specific library configurations, like turning on tensor cores. It is optimizing across the entire stack simultaneously.
This research proves that LLMs, when placed inside the right Agentic RL environment and given access to tools like compilers and profilers, do much more than just memorize C++ syntax. They systematically bridge algorithmic insight and low-level hardware performance engineering. They are learning to beat traditional compilers at their own game.
It is a massive takeaway for anyone building infrastructure today. We are moving from a paradigm where human performance experts spend weeks handwriting custom kernels to a world where an AI agent loops through 200 interaction turns in a few minutes and spits out code that leverages tensor cores flawlessly.
If we pull back and connect this to the trajectory of the broader industry, it leaves us with a rather provocative question regarding the future of hardware itself.
Oh, I like where this is going. What's the question?
Right now, we are training AI agents to understand GPU microarchitecture deeply enough to out-optimize our absolute best compilers on existing static hardware. But hardware design is inherently an iterative process of finding bottlenecks. If an AI agent can autonomously identify the exact memory bottlenecks, the register spilling, and the precise execution paths that limit software performance, how long until these same agents are used to identify bottlenecks in the hardware architecture itself? We might soon see AI agents designing the next generation of physical silicon, arranging the transistors based on the optimal code paths they themselves discovered during these RL loops.
The software agent optimizing the physical silicon it lives on. That is a wild thought to leave off on, but given the blistering pace of this research, it feels entirely plausible. Thank you all for tuning in to this deep dive into the source material. Remember to keep building, keep experimenting, and we'll catch you on the next analysis from AI Paper Podcasts.